Yeah, good. So the next talk is Elena Pourmal, who already gave a talk yesterday, so I guess needs no introduction at all. So please, I think you need to swap your screens, and we can't hear you.
Because I was not talking. Good morning. Can you hear me?
Yeah, perfect. Thanks a lot.
Okay. So good morning, everyone. It's still very early morning in Champaign. And today I will be talking about the features we are working on that are listed here. So I will give a quick intro to our small organization, our company, and talk about our effort to introduce multi-threading into HDF5, our progress on storing sparse data, and design for new storage of variable length data in HDF5. And I will also talk about integrity of data in HDF5, or so-called HDF5 encryption. So just quick introduction. Many of you know me as a member of the HDF group, but in August 2021, we spun off as a for-profit organization with a goal to raise funds for future development of HDF5. And we were very successful in raising those funds. We are currently funded by Department of Energy Small Business Administration grants. And yesterday I talked about reviving and bringing to production quality new implementation of Swimmer, and it has coding name toward robust HDF5 because DOE for 4 years refused to fund it, and finally they funded it. We will not be only productizing the Swimmer, but we will also be developing the tool to recover data from corrupted HDF5 file. And today I will be talking about our progress on two grants toward multi-threaded concurrency that we started 2 years ago and supporting sparse data. And I will show you, we finished implementation prototype of encryption, and currently are waiting for announcement if we won phase 2 grant. So if we won, we will be continuing work on enhancing encryption in HDF5. So toward multi-threaded concurrency in HDF5, as you know, HDF5 library can be thread safe, but it is not multi-threaded. It doesn't support entrance of multi-threads into HDF5 library without corrupting data in memory or data in the file. And there are several approaches to multi-threading. First approach was to just start revising and rewriting HDF5 library as is and retrofitting the code to provide multi-thread support, which is really daunting task, and we immediately, knowing dependencies between code components in HDF5 library, we decided we're not going this way. There were suggestions to us to redesign and rewrite in contemporary languages that support multi-threading, like C++11 or Rust. We'll also look into it, and once again, with amount of funding we have and the goal we had really ruled out. So we decided to leverage existing wall architecture to introduce multi-threading in HDF5 with the goal that multiple threads can enter the library and use multi-threaded wall connector to access data in HDF5. And this is kind of intermediate solution. We will be working toward completely multi-threaded library, but this is the first kind of stage, first that proves the concept that it really helps with performance and also gives us experience in converting legacy code to be multi-threaded and providing results pretty quickly. Quickly means not tens of years, but 2-3 years, and you will see results today. So approach to multi-thread that we took, it was to retrofit multi-thread support into several service packages that wall connectors use. And here I listed the packages that we have been working on. And current status that we're almost done with conversion we converted all packages except H5P that is still in testing and integration with the rest of the converted packages. We also designed changes to multi-threaded H5S package, which is responsible for selection mechanism in HDF5. And we implemented multi-threaded wall connector to read contiguous or chunk data. And I would say that this work would not be possible with the great support and help from the developers from the HDF group, because there is a lot of knowledge of the library at the HDF group. This slide just represents architecture of our solution. So we have HDF5 API, multi-threaded API, and we converted H5VL, which is wall layer, virtual object layer that redirects application calls to the native library or to the wall connector. And green box, it's multi-threaded bypass wall connector that we created that uses H5IE and CX and H5P packages. And wall connector determines if it can handle IO requests. So it is contiguous or chunk data set of fixed data types for fixed data types in HDF5 library. If not, it redirects the calls to native library, and this is where now global lock resides, or it redirects further down to through wall that uses calls to native library, and this is another global lock here to get metadata information that HDF5 library has, and then create IO requests using internal thread pool going directly to HDF5 file. If time and funding permits, we will convert VFD layer and we will redirect our IO request through VFD layer, allowing us to use with the multi-threaded wall connector all mechanism of stackable VFDs, meaning we will be able to talk to S3, say use subfiling and so on. As you see, the idea is that we're kind of slowly replacing the guts of native library that really cannot be converted to be multi-threaded with a new implementation, and this is done in stages. Currently, we are not supporting filtering, and this will be the next step. And we will be making H5S, H5T, and as I said, VFD layer multi-threaded, so we can redirect it through regular HDF5 IO route. And this is a preliminary results, fresh last results were obtained yesterday night, just a few hours ago. This is bypass wall connector. It has internal pool, so on Linux system we experimented. It shows very nice scaling for contiguous and chunk data sets when we're using thread pool from 1 thread to 12 threads, and so the maximum is around, we receive around 8 threads. So blue bar, it is performance of HDF5 library that reads by hyperslab of specified size data from HDF5 file for contiguous and chunk data set. The orange bar is bypass pool with a thread pool, and thread number of threads is indicated here. And we modified bypass wall to log access pattern in HDF5 files. So essentially offset in the file and length of IO request. And gray bar, it is a C program that also uses threads to read from those locations, mimicking IO pattern, but not having any overhead of talking to HDF5 library and internal bookkeeping that a wall connector is doing. So you see nice scaling here. And another experiment that we did, it was really have multi-threaded HDF5 application that runs with 1 to 4 to up to 16 threads. And it uses thread safe library. This is HDF5 that reads by hyperslab data from contiguous or chunk data set. Orange bar is Now, multi-threaded HDF5 application. So HDF5 application uses several threads to enter HDF5 library, to read data. Each thread has its own hyperslab to read. It creates IO request and pass it to that IO request is then routed to thread pool that does the work. And orange, it is multi-thread connection, bypass wall connector working with multi-threaded application for 4 threads and for 8 threads. And you see it's really nice scaling when we go from 1 thread to 4 threads to 8 threads. And here we're seeing a little bit slowed down, and we suspect that currently we are not, it's pretty root locking mechanism when we talk internally, wall connector talks internally to HDF5 library. So really the results are quite encouraging, and we will continue working. It's still long, a lot of work to do, but at least we show that it is worth going multi-threaded, and we hope to find more multi-threaded applications, real applications, to test our approach. So now I'll be talking very shortly about our progress on storing sparse and variable length data in HDF5. As you know, when you look at chunk data set, and data is, like shown here, is defined only a few elements of the chunk. When we store such data set in HDF5 file, all 0 elements, which may represent missing elements in the data array, will be stored in the file. Of course, compression helps to eliminate redundancy, like zeros will be, and save some storage. But with this approach, locations of the defined elements are not stored. So application has to find where were my elements that are not defined or which were defined, and do something to store those locations. So we suggested new storage called structured chunk storage that we can use for sparse data of any type, including variable length data, and also use structured chunk for storage variable length data. And the idea is that within the chunk, we not only store the elements themselves, but we store encoded selection where those elements are located in the file. For variable length data, we store the length of each element, and in this example, I have in strings, but it really can be any array of any variable length type that HDF5 supports. And of course, it's easily then extended to sparse storage for variable length. By storing encoded selection of locations of the non-zero or defined elements. Advantage of the storage is that we store more metadata about our data within data itself, and we can also, by design, we can compress such chunked storage, compressing each section with its own compression if desired. And our experiments showed that it really a lot of savings and pretty good performance. So we are currently on the stage where we have a programming model and APIs kind of settled. We have a specification of file format. We have the first design and first version of shared chunk cache implemented that we hope will have better performance than existing chunk cache, and it will include multi-threaded implementation. And we currently can write and read correctly sparse data. So a lot of work ahead of storing variable length data, but the scaffolding is already there. So we now need to add those new features. And we will be, if you want to try, we pretty soon will release the code that just will allow to use structured storage for storing sparse data of fixed data type. We're currently implementing a new APIs to compress data, and one of those APIs I talked last time has different signature to overcome the problem of passing data to HDF5 filters. Unfortunately, we found that we had some wishful thinking with design of the first API, which will easy for user to pass data to the filters, but unfortunately it will require a lot of rework in the library. So stay tuned for new public filtering APIs. And now I will be talking about integrity of data in HDF5. And for this community, and I know for many of you is kind of encryption in HDF5 sounds like why? It is open format and we're talking with FAIR principles and we want to share data and everything is true. But as you know, data integrity is not guaranteed in HDF5. It's very easy to change or compromise data stored in HDF5. And you know that many of our SVEs that were fixed in the past several years came from modified HDF5 files where just one byte was changed and then library crashes. Of course, library now is working better. A lot of work was done to prevent this, but it is a very dangerous, dangerous precedence for especially AI applications where data models are stored, intermediate steps are stored in HDF5, and essentially your simulations can go in some weird direction if something is changed or some parameters change, even it looks like a valid parameter. So encryption assures that data is data confidentiality and integrity during data transfer, storage, and computation, because we have plain text data only in memory. Design highlights of our approach to encryption to HDF5. It was implemented as VFDs, so we didn't touch library at all. And we support all features of HDF5, including partial I/O, compression, and we will be working on supporting, if we awarded phase 2, on supporting extending solution to support a parallel HDF5 library and any desired encryption methods. Current prototype supports only encryption methods that allows computation of maximum ciphertext page size from plain page, and you will see why. It is built on with HDF5 release 1.14.3 and support two symmetric key encryptions from that are available from any encryption library, but in our experiments we used GNU Creek library. And the idea is very simple. As I mentioned, we implemented as VFDs, and there are two VFDs that implement encryption. The first one is page VFD, virtual file driver, so IO driver, that divides file address in plain text pages that it is user-defined value, and translates incoming IO request to or from page IO. So in this scenario, we always perform I/O on the pages, and pages pass to encryption VFD, you see here, where we divide page into blocks. On this picture, we show the default setting of 496 bytes. We generate 128-bit vector to randomize the data first, and we store this in encryption buffer as a plain text. And you will see that in my demonstration, we store information about encryption and initialized vector and some other parameters of encryption in plain text pages in front of HDF5 data. We talk to users, they say, this is fine, this is pretty safe, because the next pages, next blocks are randomized with initial page, with initial block, and this kind of chain reaction is applied. So we encrypting blocks and we randomizing with encrypted page next block, encrypted block next next block, creating the cipher page, which increased only by 128 bytes, which you will see really increase the size of the file, but this is encryption. So encrypted page then put into the buffer, and at some point it is wrote by other VFDs in IO stack to the encrypted file. And encryption VFD handles offsets of those ciphered text pages in the encrypted file. If you want to see implementation, there is a link at the end of the my slides. There are two new files that implement this page buffer VFD and crypt VFD and page buffer VFD, and future work will be to support parallel applications, implement those as pluggable VFD, and use threads to speed up encryption. Programming model, as usual, there is some configuration of encryption and page buffer VFDs to set access property list with two new APIs, and proceed with file creation and other properties as for plain text HDF5. And on open, you have to provide a key that was used to, and of course, library should be at hand, that was used to encrypt data, and proceed with operations like for plain text HDF5 file. That's it. So now I want to switch to demo. Can you see my three windows? Can you see terminal windows? Oh, okay.
Let's see, 1, 2, 3. Yes.
Okay. So, and so let me. What I did, I just modified. I modified example program that is available in examples repo. This is a simple program that writes and reads HDF5 dataset. And what the program does first, as you see here, we're setting different. We're setting different properties of the filters that are initialization. I'm sorry, too early. So setting parameters for the configuration structures, and then passing them, and those include, for example, plain text page, cipher page size just for double checking, then cipher block size, key size by using 32-bit. Key, in our prototype, we just hard-coded just for demo purposes. Essentially, this should be, of course, stored or passed by the user somehow to the program. And those parameters, the best way will be, because we were talking in the future about stackable, pluggable VFDs, those should be passed through configuration files, because otherwise it's really a nightmare to programmatically to put it and share it with other applications. So this work is also underway, how we configure stack of pluggable VFDs. We're doing it for other projects too. So then, where is my mouse here? Then I just create a file access property list. You're very familiar with this call. First, set parameters for encryption VFD, then set parameters for page buffer using passing. Since they are sitting on each other, I have to pass information from page buffer VFD to already created FAPL. What I'm doing here, it should be right because it works. Sorry, it's too early. Oh, right. So I initialize while I'm initializing page buffer, I'm already passing through its FAPL configuration that is in set up by encryption VFD. So everything is correct. And then I'm following the regular HDF5 paradigm programming model: create file, create data space, create data set, write, and I will be able to read and write as usual, and then open the file. And once again, just to save programming space, I'm reusing FAPL that I used for encryption. In general, you cannot do it. You have to know your parameters and set them up, or they should be passed along with the key to the reading application, and then read data. So, so having said this, so now I will compile the program with H5CC, and I will run it. And it prints some data, and it created for me encrypted file. And how do, oops, let me clean. I forgot to clean from yesterday. Remove H5, and I will rerun the program. And now I will have only one encrypted file. And how do I know that file is encrypted? If I use head command on this file, an H5 crypt file, I will see information that you saw already in my structures. This is plain text, first two plain text pages that are in front of HDF5 data. And now I can use tools to read the data from HDF5 file or manipulate with encrypted data, as I usually do for working with clear text HDF5 file. So here, what I'm trying to do, first, I try to dump the content of the encrypted file, and unfortunately, H5 tools are very, or fortunately, how you look, but for demonstration purposes, I need to add extra parameter to force it to use default driver sec2, so it will not be using any encryption VFD and page buffer drivers, and program will not be able, it will not be able to print data. It will say, I cannot open the file, which of course it cannot because it's using wrong driver. But H5 dump is smart enough to go through all available drivers and use correct drivers to type the data. And this is my data, so I can read my file. Even it's encrypted, I can display the data. So what else can I do with the file? I can use H5 repack, the tool, and repack file to a clear text. So now I will have two HDF5 file, and you will see the difference in their sizes. H5, and you see, of course, encrypted file takes much more space. But now I also can just use H5 dump, right? So it will be, I will use H5 dump. I will use head command. I will not use H5 dump to show you that this is really HDF5 file. Being H5, no, I was going to use head command, head, and you will see signature, HDF5 signature. This is a clear text HDF5 file. And I can repack again and specify encryption VFD driver with H5 repack command. This is my specification of encryption VFD, and it will know that it has to use buffer VFD and encrypt the file. And once again, if I use head on H5 new file, H5, it will give me, I did something wrong. What did I do early in the morning? it should encrypt me the file. And did I run this command? Yes. So I did something wrong in the first place. Here you see file is encrypted again. There is plain text information in front of HDF5 data that I can go and dump again. So this is the end of my presentation. And I want to thank HDF5 developers who really help a lot with Sparse project and multi-threading project. Thank you, and questions.
Okay, thanks a lot. Okay, a couple of questions in the room.
Thanks, Elena. That was really interesting. I wondered about the encryption bit that you just showed. It sounded, I may have missed this, but it sounded like the main motivation was for like integrity rather than like actual secrecy. Is there a reason that you chose like a symmetric encryption approach rather than something more like a signature?
No, first of all, we are not claim that we are, encryption specialists and we know much. It was the easiest way for us to start with encryption, and in future, if there is interest, it can be extended to asymmetric encryption and more sophisticated methods. And you're absolutely almost right. It is about mostly integrity that is very important for AI and ML applications. Also, it is important for if you want to not easily share the data, or data should be shared only with people who have a key, like in industry where HDF5 is widely used, but data should be kept confidential.
It's another question in the back.
Yes, indeed, just a follow-up. In case I can actually put my signature on the data, and then I encrypt this thing, how would it work actually with multiple versions? Someone comes and wants to make a new version of this file by modifying an annotation. Obviously, he doesn't have my key. It's his new version and not my original version. Would this library also support these use cases?
We were asked to support signatures, and my understanding is that signature really, it is a separate thing. It is a separate key that will be signing encrypted file, and to read data and to manage the file, you will need another key to access data into the file that has nothing to do with the signature. We will be experimenting with this. But that was one of the requests from Department of Energy also to have signing. Once again, I'm not, we're working with HDF5 library, not with encryption. We're still learning, so I don't have, I don't know if my answer is correct. But that's what we suspect what will happen.
Thanks. There's a question online in the chat. So Alex Henderson asks, is there anything that needs to be done to incorporate the sparse storage mechanism in the main HDF5 library? Is this possible to implement as a filter?
As a filter, no. This is a new storage, and it will be transparent to the users. And we are contributing this code to main HDF5. So those features will be available in main HDF5 after the HDF group accepts our contributions. But it is not, of course, everything can be implemented as filter, but I don't know how in filter you will implement storing locations of the data. It's kind of sounds like you have to store selection somewhere. So maybe filter can be sophisticated. Probably it can be, but it is much easier. But one of the goals of creating this structured chunk storage or section storage is really, it can be extended to first many sections. For example, we can store missing data. We can store now with this approach data that is not homogeneous, because we can store elements as a blob and their data types in another section. So it opens a lot of opportunities. Plus, it solves a huge problem with current variable length data types because they cannot be compressed. They become part of metadata. That's why you cannot use Swimmer, even new Swimmer, with variable length data unless you flush data all the time, which is very expensive. So yeah, it will be an HDF5 library.
Thanks. Any further questions on this? Oh, go ahead. Okay.
Also, I forgot to mention that packages that we modified to make multi-threaded, we are contributing to HDF5 main library after we assure that they do not affect performance, nothing. And the goal is to enable not only our multi-threaded connector, but any multi-threaded connector that people may write on their own.
There's one further question or comment from the room. Yep.
Good morning, Elena. Thank you for your talk. Just have a quick question about that multi-thread concurrency, especially on the writing part. There was some benchmarks about the reading, and I was just wondering, how does it look with the writing, and how are you implementing it? Is it coming as a new API, or is it implemented within H5D write, and then it does it internally? And how do you handle the filterings?
Good question. First of all, we are focusing on H5D read only for contiguous and chunk data sets. The next step will be to do it on writing. And filtering, frankly speaking, it will be the implementation. And you remember that, so writing for, I'm still sharing my screen, right? Oh, no, I'm
Yes,
not.
yes.
Oh, no, I'm sharing. Okay. This is the slide. We still relying on HDF5 library to tell us where rely on metadata that native HDF5 library gives to us to find locations of data, and on write HDF5 library creates those, allocates space in the logical file and passes to VFD layer locations where data should go. So this is long way. We're not there yet. Good thing is that it's transparent to applications. You do not need to change your application except of introducing multi-threaded to new applications. It's the same APIs.
I understand. Thank you very much.
Mm-hmm.
Okay. So I guess it's lunchtime. So let's thank Elena again.
Thank you. Mm-hmm.